In this lecture, we're going to talk about different types of acids and bases. So previously in general chemistry, we talked about Bronsted-Lowry acids and bases, but now in elements, we're specifically going to talk about Lewis acids and Lewis bases. So it's a new definition of acids and bases. And then we will talk about hard-soft acid-base theory in the next segment, which is a theory specifically helping us understand the stability of Lewis acid-base adducts. Okay, so I want you to think back to general chemistry. What was our definition of an acid and what was our definition of a base? So pause the video for a second and write down or think about how we defined both an acid and a base. Okay, so hopefully you remember that in general chemistry, we talked about that acids were proton donors and bases were proton acceptors. So remember that if you have a water molecule, this water molecule, the electrons on it can pick up a proton, and these electrons can go onto the chlorine. And we end up forming H3O plus, or our hydronium ion. And similarly for this is acetic acid. So we talked a lot about carboxylic acids. So this is our acidic proton. And when water comes in, you can take one of these protons and then these electrons go on to the oxygen. And we form the conjugate base. So that's our proton donor, and a base is a proton acceptor. So ammonia is a good example. So here, these electrons, this lone pair on the ammonia, take a proton. These electrons go onto the oxygen, and we form hydroxide and ammonium. Okay, so those were our acids and bases that we talked about in Gen Chem 1 and 2. Chemistry of the elements, we have a more general definition of acids and bases called Lewis. So the Lewis acid-base definition is that a Lewis base is any species that can donate an electron pair to form a bond. So a Lewis base is an electron donor. So ammonia is an example of a Lewis base because it has that lone pair that it can donate. Water is a Lewis base because it has that lone pair that it can donate. And even something like bromide, so remember this was a neutral species in Gen Chem 2, but here it has lone pairs that it can donate. So a Lewis base is an electron pair donor. A Lewis acid is any species that can accept an electron pair from a Lewis base to form a bond. So some examples are BH3, boron. We talked about this in Gen Chem 1, but boron forms these electron deficient compounds. So it doesn't have a full octet. So something like ammonia or water, we'll show ammonia as an example, can donate a lone pair and form an adduct. What we're going to be talking a lot about in this class are metal ions acting as Lewis acids. So both iron 3+ or any metal with a positive charge is going to have empty orbitals that can accept electrons. So you have, in a Lewis acid-base reaction, you have the donation and acceptance of an electron pair to form a covalent bond. And this is called a coordinate covalent bond. Lewis definition opens up many metal ions as potential Lewis acids. Okay, a Lewis base must have a lone pair of electrons to donate. And it's also important to understand that any Bronsted-Lowry base is also a Lewis base. So we saw that with ammonia. Ammonia is both a Lewis base and a Bronsted-Lowry base. There are some Lewis bases, such as the bromide example, that we considered neutral in a Bronsted-Lowry fashion. So a Lewis acid must have a vacant orbital or be able to rearrange its bonds to form one, to accept a lone pair and form a new bond. So there are many substances that are not Bronsted-Lowry acids that are Lewis acids. So the biggest expansion that we hear with the Lewis definition is the classes of acids. So a lot of metal ions are now acids that we didn't consider an acid before. So this was the example that I was just showing you. Ammonia, the lone pair on ammonia can donate electrons to BF3, boron trifluoride, and form this adduct. And this is what we call a coordinate covalent bond. So boron essentially has an unoccupied p orbital that can accept a pair of electrons from nitrogen. And so because it has that unoccupied p orbital on boron, this Lewis-base reaction can take place. Okay, another example is some metal ion. Metal ions have empty orbitals that can accept electrons, say as electrons from water. So a really common Lewis acid base adduct that we see for metal ions is that they form these hydrated complexes. So this could be something like manganese 2+, and you have water that can donate electrons to form this adduct. Okay, a couple examples of Lewis acids in the wild. One is chlorophyll. Chlorophyll is a molecule that's important for photosynthesis, and its main function is to absorb light and transfer energy to other parts of the photosystem in plants. But this is chlorophyll, and in chlorophyll you have this porphyrin ring, and inside the porphyrin ring you have 3 nitrogen atoms that are each donating a lone pair to a magnesium cation. So this is an example of a Lewis acid. Magnesium's a Lewis acid and the porphyrin is the Lewis base. So this is overall a Lewis acid base adduct. Hemoglobin, or specifically the heme group in hemoglobin, is another example of a Lewis acid base adduct. So iron specifically is our Lewis acid. And again, the nitrogens from this porphyrin ring are the Lewis base. So we're going to be talking a lot more about these different types of coordination complexes, but a big key here that I want you to understand is that coordination complexes are a type of Lewis acid base adduct. And we will talk a lot more about what coordination complexes are in the next lecture. Well, we're going to talk about hard soft acid base theory, and then we'll introduce coordination complexes.